Transformers have been successful in medical image segmentation, but can have limited generalization due to single-scale self-attention. The paper introduces a multi-scale hierarchical vision transformer, MERIT, to improve generalization by computing self-attention at multiple scales. An attention-based decoder, cascaded attention decoding, CASCADE, is incorporated for further refinement of multi-stage features generated by MERIT. An effective multi-stage feature mixing loss aggregation method, MUTATION, is introduced for better model training through implicit ensembling. Experiments on two medical image segmentation benchmarks, Synapse Multi-Organ ACDC, show superior performance of MERIT over state-of-the-art methods. Figure 1 illustrates the architecture of cascaded multiscale hierarchical vision transformer, MERIT. Part A shows the cascaded MERIT backbone. It details how features from 4 stages of one backbone network are cascaded with features from the next backbone. The architecture captures multi-scale and multi-resolution features and refines them using feedback from one decoder to the next backbone. Part B illustrates the use of decoders with cascaded skip connections. Information is shared across backbones during backbone cascading, skip connections cascading, and aggregating prediction maps, which helps capture richer information than a single resolution backbone. Part C shows the aggregation of prediction maps from 2 decoders. These prediction maps are combined using specific weights to generate the final prediction map. The figure demonstrates the design and working of the cascaded MERIT, which is geared towards improving the generalizability of the model across small and large objects in an image. The architecture also incorporates an attention-based cascaded decoder, CASCADE, for multi-stage feature refinement and aggregation. The algorithm takes as input the ground truth mask Y and a list of prediction maps PI, where I ranges from 0 to n-1. An initial loss is set to 0.0. A set S is defined which contains all non-empty subsets of prediction map indices ranging from 0 to n-1. For each subset S and S, a new prediction map Y hat is initialized to 0.0. For each index I in subset S, the corresponding prediction map P, I is added to Y hat. The loss is then calculated using a loss function, for example cross-entropy, DICE, which takes the ground truth mask Y, and the newly created prediction map Y hat as input. The calculated loss is added to the initial loss. The process is repeated for all subsets in S, and the final aggregated loss is returned. The method essentially combines the available prediction maps in all possible ways to create new prediction maps, then aggregates the losses from these new maps. This allows the model to learn from a more diverse set of predictions, which may lead to better model training. The multi-scale hierarchical vision transformer, MERIT, was evaluated on medical image segmentation tasks, showing significant improvements over the baseline MaxVT architectures, Table 3. Larger resolution backbones, 256 x 256, yielded better DICE scores than 224 x 224 resolution backbones with the cascaded MERIT using 2 backbones of different resolutions, achieving the highest score, Table 4. Despite having fewer parameters and flops, tiny MERIT outperformed small MaxVT, indicating that the multi-scale self-attention mechanism was responsible for performance improvement, Table 5. The integration of cascade decoder and mutation loss aggregation further boosted the performance of MERIT architectures, Table 6. Additive aggregation in the cascade decoder and bilinear interpolation in MERIT achieved the best DICE scores, Tables 7 and 8. Figure 3 visually confirmed MERIT's superior ability to segment both small and large organs compared to the baseline MaxVT architectures.